Okay, so this chapter, extreme values, what it means is we're going to be using derivatives to find maximum and minimum points in the graphs of different functions. And then we're going to use that plus some other tricks using derivatives to help us sketch curves. So we'll do this chapter and then we'll do chapter 5, which is curve sketching, and then we'll have our next exam. So first, let's go over or review what we learned before about intervals and inequalities. There's a certain set of real numbers called intervals that occur frequently in calculus and correspond geometrically to line segments. For example, if A is less than B, then the open interval from A to B is denoted by, and so there are two different notations here. The first being our interval notation. Remember, the shape of the brackets is important. It tells you whether the n values are included or not. Or set notation. And we can do it graphically by having A to the left of B on a number line. And again, when these rounded brackets are used, that means that the n values are not included. So on a number line, we show that a value is not included by using an open dot on it and then drawing a line between the two numbers. So that is how we show on a number line that all values between A and B not inclusive would be included in the domain. If it's a closed interval, that's where we have the square brackets. That means that the n values are included. X is greater than or equal to A, less than or equal to B. So because both A and B are included, we show that with a closed dot in between or on those values with a line drawn in between. Right, so we've used this interval notation before. Round brackets mean that the n points are not included. Square brackets means that they are. So express the following intervals in terms of inequalities and then graph. So you're given as interval notation. If we write it as set notation, and we can use any variable we want, we'll just use the variable x. So because the square brackets are used, that means that the n values are included. So x is greater than or equal to 1/2, less than or equal to 4. And normally we also say that x is an element of real numbers. So on a number line, remember you always go smallest to greatest. So I can designate that point as being exactly 1/2. And the other endpoint is 4. Because the n values are included, we use a closed dot there with a line in between. For question 2, the -2 is included, but the 1 is not. So all values x such that x is greater than or equal to -2, but only less than 1. And again, x belongs to the set of real numbers. So from -2 to 1, again, the -2 is included, the 1 is not. So the open dot on the 1 shows that it's not included. Whenever you're involving infinity, it can never be included. So this says that x is greater than -4, not equal to. That's all you have to write here. You could say it's greater than -4, less than infinity if you want, but you don't need to. So on the number line, we'd have our -4 with, again, an open dot on that. And in this case, we'd have an arrow going off to the right. Whereas for number 4, you're going from -infinity to 1. The 1 is included. So we say all values of x such that x is less than or equal to 1. And again, x is an element of real numbers. So less than or equal to 1 means it's included. That's our closed dot. And in this case, we have an arrow going off to the left forever. Remember, the rules for solving inequalities are the same as the rules for equalities, except if you multiply or divide by a negative value, the inequality reverses. So we want to solve each of these and graph the solutions on a number line. So for number 1, I would subtract the x from both sides, and I would add 4 to both sides. And then when you divide both sides by a positive 5, the inequality is not reversed. And you always read from the x. So this says that x is greater than 1. So on the number line, we put a 1 on there with an open dot because it's not equal to, and an arrow going off to the right. So that's a linear inequality. This next one, though, is a quadratic inequality. Where does x squared plus 2x, where is that greater than 0? So because you've got an x squared and an x, you could factor out an x. But then how do we handle it from there? What do we do? Because we've got two factors, and the product of those two factors must be greater than 0. Well, there's a couple of ways you could do this. Because there's two factors there, okay, there's two scenarios that would give us a positive value there, meaning it's greater than 0. So that would be when both factors are greater than 0. That's one possibility. If both factors are positive, a positive times a positive will give you a positive, a number greater than 0. So here it would be x is greater than negative 2. And so you've got two conflicting statements here. One says that x must be greater than 0. The other says x must be greater than negative 2. And so the one that satisfies them both will be that x is greater than negative 2. I'm sorry, greater than 0. I apologize. All numbers greater than 0 are also greater than negative 2. But the other scenario that would work is if x is less than 0 and x is less than, or x plus 2 is also less than 0. You see, if both factors are negative, a negative times a negative will give you a positive, a number greater than 0. So you've got x is less than 0 and x is less than negative 2. Again, two conflicting statements. So the one that satisfies them both would be that x is less than negative 2. So that's one way that we can determine what the domain is for this scenario. What values of x must we have so that x squared plus 2x is always positive, greater than 0? The other option, though, would be to take the graph of x squared plus 2x. Use the graph. So that is a quadratic that opens upwards because it's a positive 1x squared. And the fact that we have it in factored form allows us to know where the x-intercepts are. They would be at 0 and negative 2. Right? If x is a factor, then x equals 0 is an x-intercept. If x plus 2 is a factor, then negative 2 is an x-intercept. So this quadratic, again, would open downwards. We don't know where the vertex is, but really we don't need to know exactly where it is. We just need to know, in this case, where's the graph above the x-axis. That's where the value of the function is greater than 0 or positive. And again, that will be where x is less than negative 2 and greater than 0. So either way, you'll get the same solution. So less than negative 2 means an open dot on negative 2 with an arrow going to the left. Greater than 0 means an open dot on 0 with an arrow going to the right. So there's the solution to that inequality and a solution on the number line. Number 3. So you've got a third degree polynomial in factored form, and we want to know where is that less than or equal to 0. So this one would be a little more difficult to do with the scenario method because you've got 3 factors and the product of them must be less than or equal to 0. That would occur if they're all negative, all 3 factors are negative, or if one of the factors are negative. And so you'd have to look at 3 different scenarios where only one of them is negative. So I think in this case, it's probably better to do a sketch of the graph because in this case, we want to know where is it on or below the x-axis because it's where the factors are less than or equal to 0. So the fact that it's in factored form does make it a little bit easier to sketch the graph because we already have our x-intercepts. If x plus 1 is a factor, that means that negative 1 is an x-intercept. If x minus 2 is a factor, positive 2 is an x-intercept. And x minus 3 is a factor, so positive 3 will be our x-intercept. There are 3 of them. This is a third degree polynomial. You might remember from Math 30-1 that if it's a third degree polynomial, you compare it to a line. If the initial term is positive, that's like a line with positive slope. It'll fall to the left, rise to the right. And that's what happens here. If you multiply the 3 x's together, that will give you your initial term of the polynomial. 1x times 1x times 1x is positive 1x cubed. So the initial term coefficient is positive. It's going to act just like a line. It's going to fall to the left and rise to the right. So the graph would look something like this. We don't know exactly where those min and max values are, but those are things that we're going to find in this chapter. Where is this maximum point? Where is that minimum point? We're going to find that using derivatives in this chapter. But for now, all we want to know is where is this graph on or below the x-axis. And so there'll be 2 different scenarios where that happens. The first will be from negative infinity to negative 1, and the negative 1 would be included because the function does equal 0 there. Our solutions will be when the function is less than or equal to 0, which means either on or below the x-axis. And the other interval where that happens will be between 2 and 3. And again, square brackets are used for these ones. So on the number line, we'll have negative 1, we'll have positive 2, we'll have positive 3. The first part of this, the negative 1 is included. So close dot, and we go to the left forever. The second part, the positive 2 and positive 3 are both included. And then we have a line drawn between them. Again, close dots because those end values are included. For number 4, again, we want to know where this third degree polynomial is only greater than 0, which means it must be above the x-axis. Once again, because positive 2 is an x-intercept, or x plus 2 is a factor, that means that negative 2 is an x-intercept, x minus 2 is a factor, as well as x minus 4. So that means positive 2 and positive 4 are also x-intercepts. Once again, this would be a third degree polynomial with an initial term of positive 1x cubed, which means again it'll act like a line with a positive slope. It'll fall to the left and rise to the right. So the sketch would look something like that. Again, we don't know exactly where those max and min points are, but we will find them later on in this chapter. And in this case, we just want to know where the graph is above the x-axis, not on it. So that'll be from negative 2 to positive 2, and those are not included. And then from positive 4 to positive infinity, where the graph is above the x-axis. So again, between -2 and +2, so open dots there with a line in between, and then greater than 4, again an open dot with a line and an arrow going to the right. So there's those solutions. So what's different about number 5 is that we're going to have to factor to find out where the x-intercepts are. So remember, we have our factor theorem and our remainder theorem. To find the first factor, we can use our potential integral zeros. In 30-1, we would use our graphing calculator to find our first x-intercept, and then convert that into our first factor, and then use synthetic division to divide. But in this case, we're not going to be able to use graphing calculators, so we need to do some guessing and testing to see where our first x-intercept is, our first zero. And they come from the factors of the constant term, in this case, -12. So what numbers multiply together to get -12? And they will be plus and minus 1, plus and minus 2, 3, 4, 6, and 12. Those are the different combinations of numbers that we would multiply together to get the constant term of -12. So if we want to know if +1 is a 0 or an x-intercept, so we can divide by x minus 1, because that's what the binomial would be that corresponds to an x-intercept of +1. But remember, we change it to x plus 1 so that we can add as we're going along using synthetic division. And in this case, you're dividing it into 1x cubed but there's no x squared term, so remember we change that to, or include that with a coefficient of 0, minus 13x minus 12. That first number is written down below, and then we multiply and add. 1 times 1 is plus 1, and then we add and get plus 1. 1 times 1 is plus 1, we add and get -12. 1 times -12 is -12, we add and get -24. So this means then that x minus 1 is not a factor. It doesn't divide evenly. If it did, we would get a remainder of 0. That's what we're trying to get. Trying to get a remainder of 0 at the end. If it gives us a remainder of 0, that means that it goes in there evenly. And in this case, it doesn't. Okay, so that was to show that that +1 was not an x-intercept. Again, that would have meant that x minus 1 is a factor, but we changed it to x plus 1 so that we could add as we went along. So let's see if -1 is a x-intercept. That would mean that x plus 1 is a factor, but we would change it to x minus 1 again so we can add as we're going along. One times negative is -1, and we add and get -1. -1 times -1 is +1, we add and get -12. -1 times -12 is +12, there we get a remainder of 0. So this means that x plus 1 is a factor. Because when we divide it, we get a remainder of 0, which means it goes in evenly. But this also gives us a quadratic factor. Okay, if x plus 1 is one factor, these three numbers give us the coefficient of the quadratic factor. In this case, we divided a third degree by a first degree polynomial. That'll give us a second degree polynomial. And again, these three numbers at the bottom give us the coefficients of the terms of that quadratic factor. It's 1x squared minus 1x minus 12, which we can factor to get x minus 4, x plus 3. And there's the complete factors of this polynomial function. So, if we were to graph it now, because we want to know in this case, where is this graph on or above the x-axis? So if we were to sketch a graph here, x plus 1 is a factor, so negative 1 is an x-intercept, as well as negative 3. That would come from the x plus 3 factor. Positive 4 is an x-intercept, which comes from the x minus 4 factor. So negative 1, negative 3, positive 4. Once again, in this case, it's a third degree polynomial, which is an odd degree. Compare it to a line. Initial term coefficient is positive 1, so it'll act just like a line with positive slope again. It'll fall to the left and rise to the right. So there's a sketch of that graph. It looks something like that. So we want to know again, where is this graph on or above the x-axis? So between negative 1 and negative 3 it is, as well as after positive 4. On or above, meaning you can include the n values in your domain, but for positive 4, you'll have an arrow going off to the right. And if you have a rational function, we can do this similar to that quadratic one that we did, where we talked about the different scenarios that we would need in order, in this case, for that rational function to be greater than 0, meaning it's positive. So there's two ways that a rational function can be positive. The first being if both the numerator and denominator are positive, which means that x would have to be greater than 1 and x would have to be greater than negative 2. And we would want to take the statement that satisfies them both, being that all numbers greater than 1 are also greater than negative 2. But the other scenario that would work to make that rational function positive would be if both numerator and denominator are negative, because a negative divided by a negative would give you positive. So here we would have x is less than 1 and x is less than negative 2. And the one that satisfies both of those scenarios, all numbers less than negative 2 are also less than 1. And so there's the solution. We have to have all values greater than 1 and less than negative 2. Again, open dots on both of these because those numbers are not included. In order for a rational function to be negative, the two scenarios would be if the top is positive and the bottom is negative, or if the top is negative and the bottom is positive. Now, in this case, what you need to realize is that the denominator x squared plus 2 is always going to be positive. That is the graph of y equals x squared shifted up 2 units. So the vertex is at 0, 2, and it goes upwards forever. So this is never negative. So this first scenario will not work because x squared plus 2 can't be negative. The only one that would work is if x minus 3 is negative and x squared plus 2 is positive. Because x squared plus 2 is always positive, which means that x would have to be less than 3 if you add the 3 to both sides. Okay, And so on our number line, we'll have 3 on there with an open dot and an arrow going off to the left. And so what you can work on, page 166, questions 1, all of 1, and then for 2, you'll just do A through C. And I will post these solutions to Google Classroom so you can check your answers. Some of you still haven't handed in that unit review, so make sure you get that done. Maybe you can work on that today and get it finished and handed in. Okay?